folks. So today is Friday the 13th, Friday the 13th, 2024. And we are going to be reviewing some Calgary rental rate data, but we're going to be using AI, that's artificial intelligence, to do the interpreting, the modeling. Specifically, we're going to be training an AI on rental rate data and then applying the AI model onto other similar data to see what kind of predictions it comes up with and how they compare against reality, as well as, really this video is going to be about walking through the process. So let's get started. We will be using Python and TensorFlow for this exercise. So let's get these packages installed, these libraries. Now I will be running through the code, but I'll be pasting it from a script that I already have ready. This way I don't have to type it all out, but we still get to kind of work through it, and it might be a little bit funner for you guys. So let's get going with this stuff. Next block. So we're importing all of our stuff. I've got this little timer up here because it'll kind of be interesting to watch as we work through things. So you can see every time I run the script, it's going to give us this. So we'll be using the TensorFlow keras. We will use some sklearn tricks, but we're not actually using the sklearn models. We'll be doing that in a separate video. Okay, so let's keep going. I'm gonna bring in my data frame next. Alright folks, so let's just take a look at this data frame that we'll be using. Again, these are Calgary rental rates. They're fairly current. And my starting data set was 4,064. We killed some outliers and managed to cut out, I think that's 25. So this is the length after getting rid of the outliers. And then we've got some descriptors here. So we've got the price here, the price per square foot here. We've got our square feet, the allowance for pets. We've got utility metrics. We've got bathroom metrics and just a bunch of other stuff. This is just a little sub descriptor. But let's take a quick look at the data frame itself. So this is before one final step of cleaning. As you can see, we've still got some dirtiness in here. But again, we're working with our price, our square feet, the allowance for dogs. We've got a calculation for price per square foot, the inclusion of utilities, and so that would largely be for apartments and condos. We've also got houses in the mix here. As you can see, we've got communities and we've got them all binary coded. We have bathrooms, we've got bedrooms plus den. We've got, again, townhouse, main floor of houses, duplex, condo, basement, apartment, and just a whole ton of communities. So that is what we're working with. So let's move on to some splitting. Alright folks, so we've got our splits. Now, there's a few things to talk about here. So again, we're dealing with a data set of 4,039 records or rows long. Now, the way that I like to split is I like to make 3 data sets. I like to split out a validation data set at the very beginning, and I save that till the end. So that way, that data never contaminates the model until testing phase at the very end. Now my other 2 data sets are the test train data sets, and so those are the ones that train, and then the model tests itself against to further train in an iterative fashion, which is what's really great about these neural nets. So that's kind of a high level rundown of what I'm doing here. And so you can see right here, this is the fraction of the original 439 that is going to be split out for validation at the very end for pure testing. This is the fraction that is going to remain pure, kind of clean. It's not going to ever contaminate the formation and development of the model and the AI. So in this case, I'm choosing 10%. I'm choosing to hold back 10% for testing at the end. And then right here, this is where I use sklearn test train split because it's just really handy. And so this will split the remaining 90% of my working data frame into the test and train populations, and I like to go with 50%. I know a lot of people conventionally will train their models on 80 or 70% and then apply that to the remaining 20 and 30% for their test. But I like to kind of start off at least with a bit of underfitting. So that's why I'm doing that. So let's move on and see where we end up. Actually, before we do move on, there is one item I want to talk about some more, and that's this number right here, the result set, or the random state. I've preset the random state right here, and I'll talk about why a little later. But the random state determines how your test and your train and your test sample sets get split. So for example, we talked about me choosing a 50-50 split and other people choosing an 80-20 or a 70-30 split. But we didn't talk about which ones end up in the 70 and the 30. Is it the first 70 and then the last 30, or is it a random mix? And so that's what this random state is. If I were to enter a number here like 50, then that would basically tell the test train split algorithm to always split in the same fashion. So you'll always end up with the same 50 and 50 split. If you do not add a number here, then it will always be random. And so you can end up with really lucky or unlucky results. That's why I like to set it as a fixed number, even though it's not really particularly important. I just like to know that it's either changing or that it's fixed or what. But I like to be in control, and I'll talk a little bit about why afterwards, a little bit later. Okay, folks. So here we're actually going to start working on what is the artificial intelligence. And so just to recap, we're using Calgary rental rate data, residential rental rate, and we're using a TensorFlow neural net. So neural nets are a subset of machine learning, which is a subset of artificial intelligence, AI. We are using TensorFlow neural net AI to model rental rates in Calgary. For anyone who doesn't know what or where Calgary is, it's a city of about 1.25 million, 1.5 million, probably closer to 1.5 million, maybe a little more. In population, it's a fairly large geographic footprint. You can see there's 5 kilometers right here. And the reason is because it's just kind of like in the prairies, so it doesn't have any geographic boundaries. It's right up against the Rocky Mountains. Many of you from around the world might recognize the town of Banff, right there. It's a famous tourism location in a national park. Again, Calgary, in the North American continent. There's some context for you. Canadian city. It's kind of like the economic center of the province of Alberta and the Western Prairies, because a lot of the energy companies that operate in the oil sands and the various oil reservoirs that exist running through Alberta, and the gas that is, well, quite frankly, spread out all over the place. So there's a little bit about Calgary. So the rental rates that we're looking at, it could be any of these houses. A lot of these will be, like there's a duplex right here. Right, see, there's a duplex. There's some regular houses. Let's take a look at some apartment buildings. This is kind of a zone with some restaurants and stuff, so like there's kind of a crummy old apartment building. This one's a little bit newer. Another crummy old one. Those ones down there are a little newer. See these ones? So these are some apartments or condos or whatever. Again, these are residential buildings right here. I'm not sure about these two actually. But this one here, this one, these ones will be residential. Right down by the river. Let's look at this part of town real quick. Oh yeah, okay. So, here we've got some row houses, right? Those are pretty nice. See here we've got like some low-rise apartment buildings, right? Some, again, a sort of a duplex. So these are the types of things that we're looking at. Calgary's got some pretty good green spaces. The economy's pretty good. We've got an international airport. Pretty close to the States. Pretty close to the national parks. Again, like I said, we have the oil companies, so Calgary's a nice place to live. Let me put it that way. So again, I've got my timer. So we had the timer for the start of the script and another one to set the time when we start the neural net. So these are just some parameters that we're setting. This is the type of model. I'm not going to go into too much detail because ultimately you can rabbit hole as much as you want on any of these items. I'm just kind of showing what's up. This is the activation function, CAF, and that is coded right here. Again, the reason I code this as a variable outside of the line items themselves, I'll go into that later, but just observe that I do it. And then my what was my, those are my epochs. They'll come later. So just be aware that E is for epochs, and for now I've set it at 20. Now, when we described our data frame, we ended up with 271 columns, but I actually ended up going with 256 on this. So this is kind of like the input shape, and you don't actually have to set an input shape, but you do have to define layers. You have to define at least a couple, I need an output layer, and what is my output? My output is one thing, right? It's a price. We're modeling rental rates, so the output is going to be one rental rate, or one per square foot rental rate, right? So how many of these layers and what each one of them looks like, for example, in terms of their input size or their activation function, is one of the things that you can tweak when you're tweaking your AI neural net model, right? So let's just run this and make sure we don't get an error. Okay, so we got our neural net start time there. Okay, so let's move on to some of the next items for the neural net model. So right here, we're going to define our optimizer and loss function. So our optimizer it's called Atom, but what it does is I'm not even gonna go into it, but Atom seems to work pretty well. I encourage you to look it up on your own and kind of figure out what all these things mean. The loss is this one's important. Well, they're all important, but this one I can talk a little bit more about. So the loss will tell you what method it's going to use to improve itself. So in this case, we're telling it measure your performance in mean standard error, and then improve yourself based on that metric, right? And then these metrics here are just metrics that I've chosen for the output, like down here, so that I can see how the model's behaving. So right here, we're just kind of putting it all together. So right here, I've got my X inputs. Right here, I've got my Y inputs. So in this case, my Y inputs are set. Let's just see, what was that? That's X train and Y train. So X train. Oh, right here, X train and Y train. So I've got my PSF, right? Okay, so right now we're not working with natural rents. We're working with per square foot rents. And it's worth noting that all of the rents, all of the 4,000 and change rents in this study are from a single snapshot in time. So there was no need to do any kind of time adjusting. It was just let's get them, and it's a snapshot, and they're all in the same point in time. Okay, so that's what we're measuring. Our validation, again, it's going to be 50-50. Our train versus our validation is going to be 50-50 split, and we're going to run through them 20 times. So what are the epochs? Again, that's this 20 that I set up here, but what exactly is that? It's just basically, it's kind of like if you were doing your real estate modeling the traditional way, and you were doing a regression, each regression that you're doing is kind of like an epoch. Maybe you decide that you want to tweak some parameters and you end up doing like 6 or 8 regressions, right? And each one you tweak a little bit, and hopefully they improve. that would be similar to doing 8 epochs, right? So here I've told the neural net model to do 20 epochs, and you can really put anything that you want. And one of the reasons that I've put these timers is so that we can see how long this stuff takes, right? So that you can see. Now you might have noticed I'm in Google Colab up here. You know, like this is Google Colab, right? So I mean, you can always experiment with switching from GPU to CPU to TPU and etc. Maybe you have a paid plan, but it's always fun to see how long these things actually take the computer. So you can see here that it's working on its first iteration, okay? See? And so as it's worked through, it's basically like outputting those results that I asked for. So just kind of like focus in on one number and watch how it evolves as we run through the epochs. See, I like to look at the mean absolute percentage error or the mean absolute error. It's just if you don't know what kind of means you're looking at, then this number really means nothing. And actually, while that's running, let's go back up. Oh, sorry, I deleted it. Never mind. We'll run it again. Don't worry, we'll get those means, folks. We'll get them. 19, 20, 20. All right, okay, let's go back and get some of those means. So our mean PSF is $2.35, okay? That is to say the mean of our fourth of the ones that ended up in, you know, the what we're working with here, it's $2.35 per square foot of rental value. So right here, this number now starts to take on some more meaning because this is telling us that our mean error is 15 cents on $2.35. So you guys can't see this on your screen, but I've got a calculator here and I'm just punching it in, and that's an error rate of 6.4%. Okay, whatever. Yeah, so you can see we've got r squareds hovering around 90, so that's decent. Anyways, you're starting to get an idea of what this is starting to be like. So let's continue on with the show. All right, folks, let's rock and roll. We're cooking with fire now. As you can see, I've thrown on I mean, like, this is the model, right? Like, this is it. So from here to here, that's the AI. Okay, that's the AI right there. That's it. That's it. There's nothing else. There's a lot that you can tweak. You can tweak your number of layers. You can tweak some of the things within your layers. And there are other attributes. You just have to look them up. You know, you can tweak your optimizer and your loss. And you can tweak how your inputs are set up, right? You can tweak the quantity of your inputs. You can tweak the test splits of your inputs. So those are all the things that you can tweak. Now I've applied the model to the validation data set. Okay, so that's xval. So let's see what xval, where xval came from. Right here. So df validate, yeah, okay, so these are the pure values. So these are the values that the model has never seen, okay? So they were cut from the population before the model started looking at the data, okay? So that's what that is. Now, let's just look at this metric. So this AI, as it's set on the data that I've shown you, took about 1 minute to run. 1 minute to run with 20 epochs. Okay, we'll do another test with some more and some less epochs after we get some results, but for now, let's just keep rolling. Rolling. Okay, so let's do some quick model diagnostics. Let's see what we get. So these are the predictions, right? So when I input the validation data set into the model, it gives me predictions. So these are the per square foot predictions for each of the rows in this data frame right here. And don't worry, I know this looks messy, but just bear with us. So here we've got some metrics here. So let's just go and look at what these items are. So that would be your absolute error, mean absolute error, and your error standard deviation. Okay, for your first two. Mean absolute error and error standard deviation. What else do we have? Absolute error, percentage mean error. Okay, just, a bunch of standard deviation and kind of like mean metrics. Considering that we're dealing with a mean per square foot value of $2.35, I would suggest that having standard deviations and errors in these ranges is not too shabby. We then go on to have the model evaluate itself using the X validation and the Y validation. So those are not my calculations. Those are the library's functions, and that's right here. Right. So we've got an R squared of 92, a mean absolute percentage error of 5.5%. Right. Mean absolute error of 13 cents on $2.35. So let's just clear this up and let's keep going, folks. Let's look at some graphs. Actually, let's get this into a separate one. There we go. What do we have? So these are the errors. You can see that for the meat and potatoes of this data set, the errors tend to be a positive error. So that would be the prediction minus the... Okay. Yeah, no, so the real minus the prediction. So that means that the prediction came up short for these ones right here. Okay, the predictions came up short, but only by about maybe 8-10%, right? In the in the lower range of the rental rates, we're having a lot of errors to the overshoot, right? A lot of errors where the prediction overshot. And then the same is true in the very high value rental rates as well. Now this is the scatter plot with predictions against their real match. So whatever the real value was in the row, this is the scatter of the prediction against that value. Now you can see here that this is pretty decent. We'll show some examples later of like bad outputs, so you can have some context, but just know that this is pretty decent. Okay, it's supposed to be in a kind of a tight diagonal line, and the slope of the line would depend on the scales of these axes, but because they're loosely the same, it should be generally a fairly tight 45-degree population. That's what we're hoping for. Okay, so let's keep going and look through some more stuff here. Let's go through some more charts. Alrighty. Okay, we've seen those ones. Now these are the training and testing scores, and they're kind of pulled out of the model. The model tracks its performance, and so this kind of shows how, as it went through the epoch iterations, the model score improved. So you can see how it has advanced through 20 epochs, and started off really bad, and then it gradually just kind of tightened up closer to 0. These all show the same thing from different perspectives, and you're looking for the lines to tighten up down, right? Tighten to tighten to tighten, like this. So there you basically have it, folks. Like, that's it. You can see the predictions against here are, they give a pretty good output. You can see the errors are within a range. There are a few big ones, but maybe there's bad data items. You know what I mean? Maybe there are irregular entries there. I haven't gone in to look at them. I could. We do have all of the values in sequential order as they were inputted available to us. So again, just focus on one of these columns, whatever one that you like, and notice how the number just sort of evolves better and better. This is the R-squared, so the closer to 1, the better. The higher the number, the better. You can see it starts off really bad, negative even, 11, 60, 70, 80, 90, 85, 85, 90, 87, 90, 91, 93, 94, 89, 92, 93. It settled on 93, folks. And again, 59 seconds. So let me go get some water and I'll be right back. Alright, folks, so I've set up a few lines here so that we can check the length of the predictions, print out the predictions themselves, check the length of the inputs that produce the predictions, check the inputs themselves, inject the predictions onto the sheet that houses the master data frame of the test validate set, and then print it out to an Excel. So just so you can see this df validate, that's that 10%, right? And this xval, like the inputs, those are the 10% that we sequestered at the very beginning, right here. See, so immediately we sequester 10% into df validate, and so df validate gets dropped from the test train index, right? Or from the test train data set. So We don't see df validate again until later. So that's where that all comes from. So let's run this. And so these are the predictions, by the way. As you can see, we have a length of predictions of 400 items. We have the predictions themselves. We have the length of the inputs and the inputs themselves. See? Ah, come on. 404 rows, 269. You know what? 269. See, what I could have done potentially. In fact, I'm actually going to do that. 259. Frig. Yeah. See, 404. See. Okay, so 259. Now, the place where that can go is right here. Yeah, see? So I'm just gonna quickly go in and do that. Now, the reason I have this in this fashion is because I want it to be a one-to-one relationship. I want the structure of the neural net to kind of be the same as the data frame. So I'm gonna run this again, and let's just be patient and see what those outputs are like with the charts. But in the meantime, we'll keep going through this item. So again, those are the predictions, these are the inputs, and this is your this. Now, I did tell it to write, there they are. So let me just kind of go here, and then, oh, where are they? No, okay, that's, okay. I'm gonna have to download these. There you go. Now, give me a moment, folks. Oh, where is it? Okay. So now hopefully that... Okay, perfect. It's just... Okay, 1 minute. Ooh, these are some pretty good R squareds. Let's just look at the charts really quick, and then we'll pop into those Excels and we'll look at some cool stuff. Actually, we might as well even just regenerate them, because I like those R squares. Okay, so these should be refreshed. Perfect. Get this. What's going on? Oh, yeah, that's because we already ran it. Okay. So this straightened out a little bit. We've got these pockets of weirdos. Again, this one took maybe a few more epochs before it kind of started acting clean. Okay, so I'm gonna be right back, folks, with some Excel action. Alright, folks, so here we have the output from the script that, you know, we were just looking at, where I attached the PSF predictions onto the inputs that were 404 items long, if I'm not mistaken. And so here you can see we've got 405 for our count, but we also have the header. So again, just so you can see, we've got 404 right here. So we've got the price. Okay, so this is the actuals, right? These are the actuals. Ah, damn it, where is it? Okay, folks, so you'll notice this is dfx, not dfvalidate. I had the wrong file open, so whatever. It's just the other one didn't have the predictions attached to it. So here's the predictions and here's the actuals, okay? So here they are. Let's just get this cleaned up a bit. There we go, ladies and gentlemen and everybody else. Okay, so let's just go like this and go like this. So again, we're seeing a similar kind of tightness, and in fact, I think this layout of these outliers here might be the same as, like, the exact same. I mean, it should be. It's the same chart. But this is a pretty straight and narrow graph here, so this is very good. The results are tight. Our predictions match our actuals quite well. In fact, let's just go through and see what some of those errors are. So we've got like 2 cents, 27 cents. See, these are all fairly good. You know, let's shoot down a few pages. And they're pretty good. They're pretty good. You know? Let's go to this column, and we have an average of 11. What did the model give us? I'm just looking at that right now. It gave us 12.5 was the model statistics. So to see 11 here, that's pretty close. Let's try a different chart. Let's just go like this and like this and spread this out a bit. That's kind of scary, folks. Gotta admit. Let's get this sorted by square footage. There we go. Maybe this is a little bit more meaningful now. So let's just get this to become the square feet. There we go. There we go, folks. So again, here we have the per square foot value, and down here we have the square footage of the rental space. So obviously we see a decreasing trend as the rentable space increases. The value of the per square foot value goes down. You know, in the extremities here, maybe because of an absence of data points, there's more deviation from the real versus the prediction. So there you have it. But the orange is the prediction. So the orange is in fact tighter than the real observed. But it tracks it quite well, as you can see. So this has been our little deviation from Python. So let's jump back into the Colab environment. Okay, so we've been through the AI portions of the modeling process front to start. We didn't go through the data pre-processing, but whatever. And we've gone through some of the outputs and done some analytics, and we did some hands-on stuff with Excel. So let's start doing some more manipulation of the model and see how the results change. And this is when I'm gonna take the opportunity to talk about why I set stuff like this outside of the model. And the reason is because I could put, for example, all of this stuff through a loop, you know, and I could iterate through maybe like 4 different activation options or 20 different epoch thingies. Or I could set a number here and then multiply this number of rows. Like I could be like this times E, right? Actually, let's do that. Let's do that and see what happens. So let's go like this actually. We will go like this and comment those out. And we'll just multiply that by E, and we'll keep our input and our output ones. So let's do this. Wait, what's going on? Okay, that's not how it works, obviously. But you get the idea. You can start to have a more tools to manipulate your code if you keep these variables outside of your model construction. What I think will be interesting to see is what happens if we comment out the outlier features. Okay, so that's been run. 236, so we have basically a whole 2 cents more on our mean. Let's run our model. And again, choose a column to focus on, whether it's your loss or your MAE or your MAPE or your R squared, and just kind of observe how it evolves as the model, the AI, the TensorFlow neural net is iterating through models. It's kind of like having 1,000 monkeys that have 1,000 monkeys, you know? And so it's not that these neural nets or machine learning models are necessarily doing anything unique. It's just that they can do so much more of it, and they'll apply it to anything indiscriminately, that they can just kind of overpower our ability to compete. Okay, so what do we got? Yeah, MAPE of 11, that's not too great. 84 on the vowels. Okay, whatever. Let's see what these graphs are like. Okay, so this doesn't feel quite as tight. You can see that our scope is expanded a bit, because before we couldn't see 5 and 6. It took about to 7 or 8 before it flattened out, so it took a little bit longer. And you'll notice that there's a little bit more noise. There's just a little bit more noise. Let's run that one more time. One more time. Now, just to explain again, what we've done is we commented out this section, and this section contains a line of code that filters out outliers above 3 standard deviations from the mean. Okay, and so we ended up losing about 5% of our data to that line. And so that's why we saw some of our metrics go down. Like our R-squareds were in the 80s more than they were in the 90s. And the metrics took more epochs to flatten out. And there was more volatility in the reflection, the measurement of the metrics. So we've got one more epoch, and then we can print out the new outputs. Let's see. Okay, what did we get? R squared of 94, 5. Ooh, this one should be good, folks. This one should be good. Interesting. See, we forgot to look at this for the last one. So you can see that an entire half of the population is experiencing errors upwards of like 20, right? 20%. So, even though this looks good, we had more volatility here. This looks like it could still use more epochs. So now that we're on that topic, let's look at and see what it's like when we add more epochs. So let's go from 20 to 50. From 20 to 50. In the meantime, let's look at some more rental properties. So in Calgary, we have a really big mall called Chinook Mall. And they get some really high rents. Like, they get really high commercial rents here. I'm not going to talk about it, but you guys can look it up if you know where to look. And so there's a few residential buildings nearby. Here they are. There we go. There's those ones. These ones. I guess the difference between an apartment and a condo is that, one, the condos, you have to pay condo fees to the condo board. And two, you might have various utilities included in your rent, whereas it's the other way around. Sorry. Yeah, no. For utilities, it's the other way around. Because in an apartment, they'll often be included in the rent, right? Or some of them will be. Whereas in a condo, if you're the owner... sorry, never mind. I'm getting tired. That's what's going on. We still have 10 more epochs. Holy jeez, folks. Oh, here's a duplex, see? Sometimes what can happen is these duplex can be converted into fourplexes. If you create a separate entrance for the basement, then you have the top level, the bottom level on both sides. So boom, all of a sudden you have a fourplex. This is an infill. So for example, this is what the houses here used to look like, the original ones. But people will, for example, buy this lot, which goes from here to here, tear down this house, and then put up something that looks like this. And then, boom, now you have two houses. So you can either rent double, or you can sell them both off. Okay, so this is done. It took 2 minutes and a half. And I don't think we really gained anything, but let's just see what the graphs look like so that you all can have a frame of reference. Okay, so it did pretty good. The errors are pretty tight. I would say within 5% and 5%, with the exception of your really high ones. What do we have here? Yeah, there's your scatter, nice little spear. And see, as you zoom out and get to more epochs, like you get to a point where it's not going to improve that much more. You know what I mean? Like you can improve from 90 to 95, and then from 95 to 98. And then, like, is it going to take you another 20 minutes of processing to get from 98 to 99? And then another day's worth of epochs to get from 99 to 99.5? So that's just always something to consider with these models. Now let's do the opposite. Let's go from 50 down to 5. So you won't have to wait long for this one. But let's see how it performs. Let's see how it performs. Okay, so the mean absolute error is probably around like 12-15%. Oh, there it is, 13%. R squared of 65. Let's see what these graphs look like. Oh yeah, so we've got chronic negative errors to the tune of 20%. We've got an irregularly shaped curve here. You can see we've got 6 on the one side and 3 on the other, so we can see that the model never really normalized. It still had a lot of work to do. And so there you have it, folks. This has been a rundown on TensorFlow neural net machine learning applied to real world rental rates in the city of Calgary. But before we wrap it up, actually, let's just do one more example with the actual rents instead of the per square foot rent. So here I've got this one. Okay, so we'll comment this one out. We'll uncomment this and we'll comment this. Now let's run that. Okay, what do we have? We've got a mean of $3,100, $2,300, $2,332 in rent for the average rental property. Now, grain of salt, folks, you saw all the different property types that we have here, so just bear that in mind. Average rental size of 1,100 square feet. Here's that 236 again. Actually, let's get these outliers back on, or rather the filter for them back on. Yeah, there we go. 23.25 for your price, 1,100 for your square feet. Yeah, there you go. Okay, so let's run the model with 12 epochs. $40 seconds, folks. That's my guess. 40 seconds. The big 4-0. Or whatever. Come on, come on. Again, now you can see this number is very large now because we're dealing with a mean rent of $2,300, right? So $340 error on 2,300. I've got a calculator out here. 342 divided by 2325. That's 15%. So that's a 15% error. Loosely reflected here. R squareds of 60. So you can see why I chose to do it with the PSF. It's just better. It works better for this data. But if you were wondering why, that's why. So here, that was fairly interesting, folks. Let's take a look here. There. So you can see that from the halfway mark backwards, the errors are on one are largely negative, whereas on the other side they're largely positive, right? So the model didn't learn so good here. Again, we've got a weird kind of scatter plot, and we've got some outlandish values, some outlandish rents here, folks. So again, this is why we convert to a standardized unit, like per square feet, and get rid of outliers. Because look at this one up here. I think there's a property in here for 4,000 square feet. No, I think there was one for 2,000 square feet and change, going for 10,000 bucks or something. It was just, there's some weird stuff in there. So that's why we convert to a standardized unit and get rid of outliers. And again, this is what it looks like when stuff doesn't work so good, or when you didn't give it on enough epochs, right? So once again, folks, I hope this was interesting. If you guys have any questions, leave them in the comments down below. I appreciate all the likes and subs that you want to give. I'm going to be doing another video exposing a large language model to the same data set, and I'm going to be doing another video on sklearn machine learning models on the same data set. So that's different than the TensorFlow neural nets, but it's the same kind of idea. The large language models is a complete different concept. That's a whole nother thing. So stay tuned for both of those other videos. I anticipate having them out this weekend. So thank you for tuning in.